Hello friends, welcome to my channel, and today we're going to solve the mathematical physics paper. This is part 2. Part 1 link of the part 1 is given in the description box, where I have solved from question number 1 to question number twice to question number 2a. So today we're going to start from 2b, right? So this is the mathematical physics paper of BSc3rd SEM set by Dibrugarh University of the year 2020. For the physics honors students, C5 paper. So before we start, please subscribe the channel if you are new to my channel, and stay connected. Also hit the bell icon so that when next part will be uploaded, you get notified, because I can't complete this whole paper in one single video. So that's why please hit the thumbs up button and bell icon as well, and also share the video if you like my videos. So now let's start. And one more important thing, please go to the community post and participate in the poll. So here is the first question. Find the value of summation from n to infinity of 1 by n square using Fourier series. So let me solve this one first. So solution: suppose we have a function. So as we are taking here 1 by n square, so let us have a function x square, which is f of x, right? So f of x is equal to, suppose, x square. See, we have a function f of x is equal to x square, right? So now you see Fourier series in the interval. Let me take the interval minus pi to plus pi. So Fourier series for this function. Okay, so Fourier series for f of x is equal to a naught by 2. So let me write below. So f of x will be equal to a naught by 2 plus summation from n is equal to 1 to infinity an cos nx plus b n sin nx. So this is the Fourier series for the function f of x. So now let's find the coefficient a naught. Let's find the value of a naught. So that's given by 1 by pi integration minus pi to plus pi, then f of x dx, right? So here it will be 1 by pi minus pi to plus pi, right? Then here our f of x, we have taken x square, right? So let's put here x square dx. So if you integrate this, then what are you gonna get? So that will be equal to 1 by pi x cubed by 3 minus pi to plus pi, and put those minus pi and plus pi here, upper and lower limits. Then you will get 1 by pi into pi cube plus pi cube by 3. So pi cube plus pi cube, that's gonna be 2 pi cube, and this pi cancels pi cube to give pi square. So that's why the value of a naught will be 2 pi square by 3. That will be the value of a naught, right? So now let's evaluate the value of an. Let's find the value of an. So if you find the value of an, so that will be given by 1 by pi integration minus pi to plus pi f of x. Then here we have taken cos nx, right? So that's gonna cos nx dx. That's what we will get. So again, f of x, let's put x square here. So then what you will get, integration 1 by pi integration minus pi to plus pi, and this is x square cos n x dx. So if you integrate using this rule, integration u v dx, that's going to be equal to u integration of v dx minus derivative of u integration of v dx, then whole integration of this whole, right? So if you apply this rule, then what you will get. Okay, let me show you the integration here. So suppose you have taken integration x square cos nx dx. Now consider this one as u and this one as v, right? So if you apply this formula, then what you will get, x square integration of cos nx dx minus integration derivative of x square, then integration again cos nx dx, right? You will get this. So let me just arrange it. Okay, so that's what we will get. Now you see, integration of cos nx dx, that's going to be sin nx by n, then minus derivative of x square. So derivative of x square, that's going to be twice x, then integration of cos nx dx, again sin nx by n dx. Now again, here we are going to apply the same rule. If you repeat this rule here, then the final result will be like this, taking x as a u and this one as a v, right? So final result will be this, x square sin nx by n minus twice x cos nx by n square. So here it should be plus, then minus twice sin nx by n cube. So this is going to be the result of this integration. So now let me write here directly this result. Okay, so we have got x square after integration sin nx by n plus twice x cos nx by n square minus 2 sin nx by n cube. That's what we got, right? And our interval is minus pi to plus pi, right? And here you see, we know that value of sin pi is 0, so these two terms gonna be equal to 0 when you use these intervals, right? So only we will left with this middle term. So what we will get, 1 by pi, and if you put the upper and lower limits in the middle term, then what you will get, you will get 2 pi cos n pi by n square, then minus, if you put here minus pi, then you will get this plus, and again 2 pi cos n pi, because cos minus theta is plus cos theta, right? So that's why you will get the same terms. So that's going to be equal to 1 by pi twice into 2 pi cos nx, n pi by n square. So here you can see clearly pi cancel, so you will get 2 to the 4 cos n pi by n square. That's what you will get, right? So, and the solution of cos n pi, that's the value of cos n pi will be given by 4 by n square, this value will be given, value of cos n pi will be given by minus 1 whole to the power n, right? So if you see that so we have got an, we have got a naught, but we need to find bn now. Let me show you how to find bn. So let's go to another slide. Now bn will be given by 1 by pi integration minus pi to plus pi f of x d sorry, not dx, sine nx dx. Now 1 by pi f of x is our x square minus pi to pi x square sine nx dx. That's what we will get, right? Now if you integrate this again using this u into v rule, right, again taking x square as u and sine nx as v, then if you use that formula wherever it is applicable, so then as I have already shown the integration of x square cos nx, so I'm not going to show this time. Just I'm going to write the result directly, and that's gonna be the result gonna be minus x square cos nx by n plus twice x sine nx by n square, then plus 2 cos nx by n cube. So this is going to be the result, and the interval is minus pi to plus pi, right? If you put the upper and lower limit, then you see the middle term, that sine pi is 0, so this middle term is going to be 0. We will left with these two terms only, and let's put the upper and lower limit, and let me write the result. Then what you will get, so you can see when we put pi here, then we get this, and when you put minus pi here, sorry, not here instead of x, then cos n minus pi, that's gonna be cos n pi again, and here we have x square, so minus pi square, and this should be minus this minus this minus, we have got this plus, right? So hope you have understood this. Now you can see clearly that let me clean this part. So these parts cancel, then again put pi here, and then subtract the value after putting minus pi, whatever you will get, subtract that one, then putting pi we have got this, and putting minus pi we have got this value, and they will be also cancelled. So finally we have got 1 by pi is equal to 0, 1 by pi into 0, that's gonna be 0, so bn we have got 0. So what are the values we have got? We have got a naught is equal to 2 pi square by 3. We have got an is equal to 4 minus 1 whole to the power n by n square, and we have got bn is equal to 0. Now let us use these values in the Fourier series. Here you see, so this is the series we have considered here. This is the series, let it be equation number 1. So let us put the value of a naught, an and bn. So, and doing so, what we will get, so if you put these values, then you will get, let me write here. So this is the equation number 1. Let us put the values of putting a naught is equal to, we have got a naught is equal to 2 pi square by 3, and an we have got 4 into minus 1 to the power n by n square, and we had got bn is equal to 0. So if you put those here, bn is 0, then this part will be 0, right? So now if you put here an, and a naught is equal to 2 pi square by 3, then these two will be cancelled with this, right? So then f of x will be equal to pi square by 3 plus 4 summation n is equal to 1 to infinity, you will get minus 1 whole to the power n by n square cos n x. That's what you will get. Now you see, we have considered that f of x is equal to x square. So if you put x is equal to pi, right? So as we have taken f of x is equal to x square, then the left hand side will be pi square, and on the other side you will get pi square by 3 plus 4 summation n is equal to 1 up to infinity minus 1 to the power n by n square, and cos n pi, as this x is replaced by pi, so cos n pi is again minus 1 to the power n, right? If you multiply minus 1 to the power n minus 1 to the power n, then it's gonna give you minus 1 to the power n whole to the power 2, right? So that's why this is gonna be always plus 1, right? So our result will be pi square by 3 plus 4 into summation n is equal to 1 to infinity 1 by n square. So that's going to be equal to 4 summation from n is equal to 1 to infinity 1 by n square. That's going to give you pi square minus pi square by 3. This is brought to this left side, right? So then it's going to give you 2 pi square by 3, right? So this implies summation from n is equal to 1 to infinity 1 by n square is equal to 2 pi square by 4 into 3. That's going to be cancelled by 2. So we have got summation from n is equal to 1 to infinity 1 by n square, that is equal to 1 by 6 pi square by 6. So that is our answer. That's how we can solve. So this is our answer. So hope you have understood this. Now let's move on to next question. So this is our next question, means the same question. So we had to solve the first one or this one. So here, expand the Fourier series of the periodic function f of x with the period twice l in the interval minus l to plus l, where f of x is mod of x. So first let me write the given function f of x is equal to mod of x, so which can be defined as minus x when x is greater than minus l and less than 0, because the interval is given here minus l to plus l, right? Then it is plus x when x is less than plus l greater than 0, right? So we can write this way. And if you find minus f of minus x, then it can be written as minus of minus x when minus x is greater than minus l, right, and less than 0, and minus of plus x when x is greater than 0 and less than l, right? So you see, you can change the interval. Here you see, if you change the sign, then you will get x greater than 0 less than l, right, less than l. And then if you change this sign of these two, then what you will get, x is greater than minus l less than 0. And now you see, if you compare the intervals, x is greater than 0 less than L. If you compare these two intervals and their corresponding value, minus of minus x is plus x, right? Is plus x. Then if you compare this one with this interval, so and their corresponding values are minus x and here also minus x. So that means we can write from these two results. So let me clean this a little bit. So okay, so this is suppose equation number 1 and this is suppose equation number 2. So from 1 and 2 we can say that f of x is equal to f of minus x. If so, then the function f of x is even function, right? This is an even function. So hope you have understood this. Now let's find the Fourier series. We know that the Fourier series for the function for a function. So Fourier series for a function f of x in the interval minus pi to plus pi is given by this f of x a naught by 2 summation a n cos nx plus b sin nx, b n sin nx. So that's what we get. So now you see, let's move on to next slide. Before going to the next slide, let me write here something. So now you see, let us suppose we have a function f of y, right, which is equal to function of L, small l, by pi into y, right? Because you see, this Fourier series is for the interval minus pi to plus pi. Now we need to change this interval to minus l to plus l, right? So that's why what we have considered that y is equal to pi by l x. That means if you put here plus l, then you will get y is equal to l. If you put minus l here, then y is equal to, you will get minus l. So that's why we have considered that way, right? So now if you put the value of y here, then you will get f of x is equal to f of y, right? And if you find dy by dx, then what you will get, pi by l, which means dy is equal to pi by l dx, right? So we're going to use these values in this equation. Now one more thing, if you write the Fourier series for this f of y, f of x is equal to capital F of y, then you can write a naught by 2 summation plus summation from n is equal to 1 to infinity a n cos n y plus b n sin n y, right? You can write this way. This is the Fourier series. So let me give it equation number 1. This is suppose your equation number 1. So hope you have understood this. Let's take a new slide. Now you see, coefficient of a naught for this Fourier series will be given by, let me show here, a naught will be given by 1 by pi minus pi to plus pi f of y dy, then that's going to be equal to 1 by pi. If you change the interval minus l to plus l, then you have to put y is equal to pi by l into x, right? Then you will get f of x pi by l, and dy is, pi by l into x, right? So f of here we have got f of x is equal to f of y. So we have replaced the capital F of y by small f of x, right? So then here this pi cancel, so this should be dx, right? This should be dx. So we will get 1 by L integration minus L to plus L f of x dx. Now for even function, if the interval is minus L to plus L, minus L to plus L, interval is minus L to plus L, that's why you can write 2 by L 0 to L f of x dx. The region is f of x is even function, right? Now here you see f of x, we know that is x, so 2 by L, so we have taken the function f of x, which is equal to minus x for x less than 0 greater than minus L, and plus x, x greater than 0 and less than L. So for 0 to L, so f of x is x, right? So that is why we will get here integration 0 to L x dx, and if you evaluate this, then you're gonna get 2 by L x square by 2 0 to L, and if you put the interval here L, then you will get 2 by L, so L square by 2, which is equal to L, because these two will be cancelled and L will cancel L square to give L, right? Similarly, we can find an. Let's find first an. So an will be equal to 1 by pi integration minus pi to plus pi capital F of y dy, not dy, here you have to write cos n y dy. Then again, if you replace this y by pi L by x, then you can get 1 by pi integration from minus L to plus L f of x cos n pi x by L dx. So here dy will be replaced by instead of dy will be replaced by pi by L dx, right? So that's what we will get, right? So hope you have understood this. So now you see here also this pi cancel and 1 by will be taken out, so you will get 1 by L integration from minus L to plus L f of x cos of n pi x by L dx, right? So as again f of x is even function, we can write this as 2 by L, then the interval will be changed to 0 to L f of x cos n pi x by L dx, right? So this should be cos n pi x by L, right, dx, right? So here you see f of x, this f of x is nothing but x, so we will get 2 by L integration 0 to L by x cos n pi x by L dx. Now let us integrate this. So if you integrate this, then you will get, let me take a new slide, okay? So let me rewrite this equation number 2 in the new slide as well. Sorry, not equation number 2, equation number 1. So I have written equation number 1, and we have already got a naught is equal to L. So now we are calculating an. So an we have got, this is an, right? Let me write this result on the other side. So value of an we had got 2 by L 0 to L x cos n pi x by l dx. If you integrate this, then you're gonna get 2 by l x sine n pi x by l by n pi by l minus, sorry, not minus, that should be plus again, cos n pi x by l by n square pi square by l square. And in order to integrate this, we have used this rule, right? Taking this one as u and this one as v, apply this formula, then you will get this result, right? So this is from 0 to l, right? So now you see 0 to l. So if you put this, if you replace this x by l, this l will be cancelled, then sine n pi, that's going to be equal to 0. So that's why this part of this result will be 0, right? So that's why our result will be 2l into l square by n square pi square cos n pi. If you put l here, by l will be gone, so you will get cos n pi only, minus, then cos 0 is 0, so that's why cos 0 is 1, so that's why there will be minus 1. So hope you have understood this. So here cancel the terms which can be cancelled, right? And we know the value of cos n pi is minus 1 to the power n, right? So after simplification, we will get a n is equal to 2l by n square pi square minus n to the power n minus 1, right? So now you see, for n is equal to 2, 4, 6 for n is equal to even. If you put even value, even power here, this minus 1 to the power even power, that's gonna be plus 1, right? And minus 1 to the power 2, minus 1 to the power 4, for even power, its value will be plus 1, right? If it is plus 1, this will be cancelled by this minus 1, giving you 0, right? So that's why an will be equal to 0 for n is equal to even number. Alright, and for odd numbers, you will get minus 1 to the power n. For n odd, you will get this is equal to minus 1. That's why this gonna be equal to minus 2, right? So that's why what we will get, 2l by n square pi square minus 2. That's going to be minus 4 by l n square pi square for n is equal to odd, right? So now you see, for even function, remember in this Fourier series, for even function, this b naught, value of b naught will be, bn will be always 0 for f of x is even, right? So now you see, we have got the values, a naught, value of a naught, value of an, that is equal to this, and we have got the value of bn, right? So let's put these values in this equation number 1. So putting the values of a naught, an, and bn, also y is equal to pi by l into x in equation number 1, then what you will get? So you will get f of x is equal to a naught, we have got l, so l by 2, right? Minus we get minus 4 l by pi square, then summation n is equal to 1 to infinity 1 by n square cos this ny cos this ny will be n pi x by L, right? That's what we will get. Okay, so this is for only odd, n is equal to odd numbers only, right? Because otherwise if n is even, this term will be again 0, right? So from now if you put the odd values, then here you say, let me write here bracket. Okay, this is the plus, right? So then you will get L by 2 minus 4L pi square, then you will get cos pi x by L plus cos 3 pi x by L by again 3 square plus cos of 5 pi x by L. So this is the angle, okay, right, by 5 square. So that's how we will get. So this is the required series. This is the required series. So hope you have understood this. Now let's move on to the next question. So our next question is to prove this. So now also find the value of p2 x. So let me show you how. So now let us consider that this is v, x square minus 1 whole to the power n is equal to suppose v. Okay, so let me consider that way. Then dv dx, dv by dx, then you will get n into x to the power 2 minus 1 whole to the power n minus 1. That's what you will get, right? Then again function of function twice x, right? So if you multiply both sides by x square minus 1, x square minus 1 v by dx. So let me write it clearly, x square minus 1 dv by dx. And if you multiply here also x square minus 1, then this power gonna be x to the power n, right? N into x square minus 1 whole to the power n. Then you can write this is as twice x, right? So now you can see again, instead of this part we can write b, right? So that's why we can write x square minus 1 dv by dx is equal to twice n vx. That's what we will get. This is suppose let me take this one as equation number 1 and this is as equation number 2. Now if you differentiate the equation number 2 n plus 1 times by Levin's theorem, okay, using Levin's theorem, or rule, you can say Levin's rule. Let us differentiate equation number 2 n plus 1 times. So if you differentiate, the Levin's theorem is given by the x of suppose u and v. There are two functions. If you want to differentiate n times, right, if you differentiate n times, then what you're gonna get? So you're gonna get u and derivative of this one dn by dx to the power n. So nth order derivative of v with respect to x, then you will get uh, so here is the Levin's rule that we are going to apply. So as we are going to differentiate it n plus 1 times, so instead of n there will be n plus 1, and there is already one more differential coefficient, so it will be n plus 2, right? So we will get, if you differentiate this equation number 2, you will get, so applying Levin's theorem, we have got this. So here you see, so here we have n plus 2 to order derivative of b, and 0th order derivative of this. That means in the first term we differentiate only the second function. Here you see, not the first function. This is the first function. In the next term we differentiate the first function, that u, we differentiate it once. In the next term we differentiate it twice, then so on, right? And here you see, if you have differentiated v n times, in the next term you should differentiate it n minus 1 term. That means order of the derivative will be decreased by 1 in each step, right? And for u, for the first function u, it will be increased by 1, right? So that is the logic we're gonna apply here. And you see, if you differentiate it once, in the next step you will get twice x. In the next step, if you differentiate it again, you will get 2. So in the next step you will get 0. That's why the remaining terms will be 0. So similarly here also, on the left right hand side also, we have applied the same rule here. So we have got this result. So this is suppose equation number 3. Before going to equation number, give you equation number 3, let me simplify this. Okay, so let me simplify this. Now you see, if you bring the right hand side to the left hand side, then from this first and the second of the left hand side, from here we can take this part common, this one, and x and 2 we can take common, right? And from these terms, these two terms, we can take this common, right? And also we can take 2 common, right? So let's do so. Just let me take another slide. Okay, so here you see what we will get after simplification. Let me write the result directly. So after rearrangement and taking common, we have got this result. Now you see, if you simplify this, x square minus 1 now you see, from here you will get and its value will be equal to 1. If you evaluate this, then you will get 1, right? Twice x. So we have got twice x, then the n plus 1 order derivative with respect to x of b. Then you will get, so that's gonna be minus n into n plus 1, right? So if you evaluate this combination and multiply it by 2, then you will get this result. So this is what we will get. Now if you replace nth order derivative of b with respect to x by y, then this equation, so let it be suppose equation number 3. So here we have given this is 1, this is 2, so this is suppose 3. So this is 3. So then equation number 3 implies, and if you take replace this one as well as take minus common from these terms, right? Then, or you can assume that multiplying minus 1 on both sides, then you will get 1 minus x square. So second order derivative of y with respect to x, then minus twice x y is equal to 0. So what we have done, we have replaced nth order derivative of v by y, and we have multiplied -1 on both sides of equation number 3. So we have got this equation, which is nothing but Legendre's equation, right? So we can say that for this equation, y is equal to nth order derivative of v with respect to x is a solution of Legendre equation, right? So we can write capital C, which is a constant, nth order derivative of v with respect to x is equal to, so Pn x, where Pn is Legendre polynomial, right? So now you see, this is suppose equation number 4. So let's move on to next slide. I'm gonna show there what I'm gonna do here. So let me just copy this one. So here you see, so the last step we have done this. So now you see that we had considered v is equal to x square minus 1 whole to the power n, which can be written as x plus 1 into x minus 1 whole to the power n, right? Or you can write here and here also. Okay, now if you differentiate again n times, if you apply the same rule, Leibniz theorem, so then what you will get? You will get 1x plus 1 and whole to the power n, derivative of x minus 1 whole to the power n, and so you're gonna get this after differentiating this one n times using the same Leibniz theorem. So now if you put 0, if you put 1, putting 1, so before you put 1, let me show you one thing. So now if you differentiate x minus 1 whole to the power n once, then you will get n into x minus 1 whole to the power n minus 1. If you differentiate it again, if you find a second order derivative, if you differentiate it again, then you will get n into n minus 1, then x minus 1 whole to the power n minus 2. And if you continue this way, and if you find the n minus 1 order derivative of the same function x minus 1 whole to the power n, then you will get n into n minus 1 and dot x to the power n minus 1 whole to the power n minus 1. That means that's gonna be to the power 1, right? So in the next term, if you differentiate n times, then what you will get? You will get, if you differentiate n times x minus 1 whole to the power n, then you will get n into n minus 1 into n minus 2 into dot so on x to the power then here you will get 1, then x to the power x minus 1 whole to the power, you will get 0, right? You will get 0. So now you see n into n minus 1, n into n minus 1, n minus 2 up to 1. This is nothing but factorial n, right? And anything to the power 0 is 1, right? So factorial n into 1, that's going to be factorial n. So here from this part, this result of this part, you will get factorial n, right? This is equal to factorial n. So if you put x is equal to, putting x equal to 1, then you will get this is equal to 1 plus 1 whole to the power n factorial n. So this value is factorial n. So in the remaining parts, you see, if you differentiate this x minus 1 whole to the power n minus 1 times, you will get x minus 1 as a factor, right? Then in the next time you will get x minus 1 whole square as a factor, and in x minus 1 if you put 1, then you will get if you put x is equal to 1, you will get 0, right? So that's why remaining terms will be 0. So hope you have understood this. So let me clean this part. Okay, now you see, so just let me clean it. This is gonna be equal to factorial 2 to the power n factorial n, right? Just let me multiply both sides by this. Just do one thing, just use this result here in equation number 4, right? Using this result in equation number 4, so what we will get, capital C, which is a constant. So C is a constant, let me write here. So you will get 2 to the power n factorial n, so you will get Pn of x, right? So here it should be Pn of x, Pn of x. So this implies one more thing. So we have used here, this is for x is equal to 1, right? So you have to put here 1, and value of Pn of 1 is equal to 1, right? So you will get C into this 2 to the power n factorial n is equal to 1, since Pn of 1 is equal to 1, right? So then the value of C will be, from this step, let me write the next step here. So the value of C will be 1 by 2 to the power n into factorial n. That's what you will get. Now use this value of C, in 4, in this equation 4 again. Then what you will get, let me take another slide. So equation number 4 was C into nth order derivative of b by with respect to x, that is Pn of x, right? So if you put the value of C, that we have got C is equal to 1 by factorial to, sorry, not factorial, to 2 to the power n into factorial n. If you use that value, right, just using or putting the value of capital C in equation number 4, then you will get this result, right? You're gonna get this result. So this is what we need to prove, right? So Pn of x is equal to, so this is the question, if you see the question, right? So that's what we needed to prove, right? So and v, this v is nothing but, v can be replaced by this x square minus 1 whole to the power n, right? So here we will get x square minus 1 whole to the power n, right? So you are also asked to find first let me write, it is proved, and you are asked to find P2 of x. So if you put n is equal to 2 here, you will get 2 square, 2 factorial, then second order derivative of this x square minus 1 whole to the power n, right? So n will be n square here, just then what you will get, then you can see factorial 2 is 2, simply 2 into 1 2, and 2 square 4, so 2 4s are 8. Here you will get 8. If you differentiate it twice, then what you will get? First, let us find the derivative of x square minus 1 whole to the power 2. Then it's gonna give you 2 into x square minus 1, and function of function, so here twice x, so it's gonna be 4x into x square minus 1. If you differentiate it again, if you find a second order derivative of the same function, that means if you want to differentiate it again, then what you will get? If you just differentiate this once more time, then first function 4x, derivative of second function, that is twice x again, then second function, that is x square minus 1, derivative of the first function, that will gonna be 4, right? So here you will get 8x square plus, so we should have written here plus, so plus 4x square minus 4, and that's gonna give you 12x square minus 4, right? So 12x square minus 4, that's what we will get. So hope you have understood this is the answer. So hope you have understood all these things, and remaining questions will be explained in the next video, next part. So hit the bell icon and subscribe the channel, so you get notified in the next video when the next video will be uploaded. And if you think this is helpful, then share with your friends and hit the thumbs up button as well. So stay connected and see you in the next video. Thank you.